This is the companion for Chapter 22. This chapter I view as more of a bridge. We're going to wrap up what we learned about electrostatics and electrodynamics and magnetism. And then it's going to introduce traveling electromagnetic waves, which we call light. And, the various forms of light just depend on the frequency. That's basically what this section is all about. And it's going to be the introduction for something that we'll see for the next few chapters. And really, when we get into modern physics later on in the book, a lot of what we know about atoms, about the crazy world of the small, comes from what we know about light. So this was foundational in that without this, we wouldn't understand how to interpret what we see around us. Well, let's start with these things that we call Maxwell's equations. And I don't expect you to know these in this form. I like talking about them like this. The book only gives them in sentences, and so I'll give you the sentences while I talk through the equations. This has symbols that you will never have seen before, and that's okay. This is just so that we can talk through them like the book does, but we've got some kind of a picture. So, Gauss's law, we actually skipped the section on Gauss's law, but it wasn't anything groundbreaking. It was about electric field. And what it says, this operator here, this little thing in math, means where do the field lines, in this case electric field lines, start. And this is a charge density. And so when you have positive charges, the field lines start there. We knew that, right? So this first one is just saying field lines start on positive charges, end on negative charges. So this is nothing new. The second one says magnetic field lines don't have a start or an end. They always form complete loops. And that's something else that we knew. If we've got a current carrying wire, for example, then we're going to have, let me draw the current. I want it out of the page here. So if we have a current carrying wire, it creates magnetic fields that never start or end. They always form complete loops. Doesn't mean they're useless. We still want to know about them because they can exert forces on moving charges. But that's what that equation's telling us. The next one says you can also create an electric field, and this tells you something about how the direction's a little bit different in this case. You can create electric fields by changing the magnetic field. That's what this change in magnetic field over the change in time means. This symbol means change. Okay, so we can either have charges, or if we're in a region where there are no charges or where the charges are balanced, you can also change the magnetic field, and that creates an electric field. That's pretty cool. This we saw in the induction. Remember, you saw that the induced voltage is equal to minus the number of coils times the change in flux over the change in time. This might look similar. Flux depends on magnetic field, and the V tells you about the electric field in that region. That's what makes the charges move. It accelerates them. And so this, once again, we've got a new way to create electric field by changing magnetic field. Now it works both ways. So let's come down here. Another way to create magnetic fields is to change electric fields. And so this one is completely new for this section. We never saw this before. This one we already knew. This is the same thing I drew up here. I've got a current, and the J is the symbol for current. Just think of it as I. Okay. So the current can create a magnetic field, but a changing electric field can also create a magnetic field. And this was pretty new. It's new to us for sure. But what it tells you is that even in places where you don't have charge, so the current is necessarily zero if you don't have any charge, in places like that, you can still get a magnetic field if you change the electric field in that region of space. And so, I'm going to get an animation really fast so you can see this. Alright, here's a representation of Maxwell's laws in action. We have currents flowing in this wire. This gray thing is a wire, like a broadcast antenna. That's really what they're simulating here. Let me pause it really quickly and just show you. Okay, the yellow lines inside the conductor tell you the direction of the current. So right now the current is flowing downward. That means positive charges are accumulating over here. There's no wire to connect this circuit, and so they just have to pile up down here. What that does, these little green arrows off to the side are the electric field. And when you have extra positive charges here, if you remember, positive charges give you electric fields. So we've got extra positive charges. These electric field lines begin on the positive charges and end on the negative charges up here. Now, this current also creates a magnetic field. And we can use the right-hand rule to figure out what direction that's in. If you point your thumb in the down direction, then your fingers will curl into the screen on the left of the wire and out of the screen to the right of the wire. The red means into, magnetic field into the board or the screen, and the green means magnetic field out of the screen. Now these can't travel faster than the speed of light. This is another concept that was introduced in this, that these equations, when you put them together, they predict a wave that travels at the speed c equal to the electric field over the magnetic field in any region of space. You can plug in what the electric and the magnetic fields will be, and you get that the speed of light is 1 over the square root of epsilon naught mu naught, and these are the same epsilon naught and mu naught that we saw throughout chapter 20 and 21. Well, really, since the beginning of the semester we saw epsilon naught, and now in the magnetism chapters we've seen mu naught. And it equals, or it's approximately equal to 3 times 10 to the 8 meters per second. It's probably a good time to just review how you would find the wavelength of a wave that's traveling at a certain speed. If you know the frequency, the relationship is that the speed is the wavelength times the frequency. Alright, so one wavelength, let's see, let's call it yellow. Okay, one wavelength is from one part of the wave through a complete cycle to where you get to that position again. So it would be from here to here. The frequency tells you if you just sat and watched a point, so you sit at one point in space as this wave travels past with speed c in this case, that tells you how many of these wave crests would pass. So you'd count 1, 2, 3, 4, 5. Okay, they usually pass much faster than you can count. For example, visible light has a frequency of, I better make sure, visible light has a frequency in the 10 to the 15 hertz range. So a 1 with 15 zeros after, that's how many peaks you would count if you could do it. Alright, so if you need to remember how waves work, it didn't talk much about it in this chapter, but you saw it in 105, so hopefully you remember that. Perhaps I'll make sure to have a video on waves posted online as well. But let's look at, now that we understand what light is, I mean really, it's as simple as these electric and magnetic fields traveling through space. You just zoom out here so you can see, I mean these things will just travel pretty much forever. You do have to remember, though, that you have a certain amount of power emitted by your antenna or whatever it is, and it will spread itself over more and more area as you get further away from the source of light. And so this is why the stars that emit much more light than our sun look dimmer to us, because we're light years away from them instead of just light minutes like we are away from our sun. One more thing that I wanted to just emphasize: the way you create light is you wiggle charges back and forth. This right here, okay, sorry. This right here gives you an in. It gives you a way to create electromagnetic waves, because by driving a current through a wire back and forth, that creates a constantly changing magnetic field. Constantly changing magnetic field creates a constantly changing electric field, which creates a constantly changing magnetic field. So this is the start, and then the rest of these equations will keep the wave going even where there's no charge to keep it going. It's pretty amazing stuff. And so light can propagate where there is no material whatsoever. It doesn't need charges to move. As you can see here, this is empty space. There are no charges, and the light wave moves there. Now, just to show you, if you were driving in your car and you wanted to pick up the signal from this, then you have an antenna that the electric fields in the wave will drive a current back and forth. Can you see? Down, now up, and then down. And then that potential difference, which is created by sloshing the charge back and forth in your antenna, your car's antenna, is what your radio uses to interpret what's being broadcast from the antenna that's far away. All right, let's look at the electromagnetic spectrum. The book throws a figure up and talks about it. We'll just spend a minute talking through these things. So radio and TV, they're usually in the kilometer to meter kind of range. AM, down in Utah there's a station that's 1160 kilohertz. So that would be right here at 10 to the 6 hertz, because kilohertz, move the decimal 3 times and you've got megahertz. So 1 million hertz is AM, more or less. FM is like, if you listen to 100.1, that will be in megahertz. So this is AM, and I should erase that dot so I don't confuse myself. And then FM radio is at about 100 megahertz. So it's right up here at 10 to the 8, around that range, plus or minus 10%. And then, okay, let's keep going. Some of these boundaries, they draw them. They're not really set in stone. And, I'm sure, like the FCC has specific regulations for what is considered UHF, for example. Once you get to the boundary of some of these other ones, you just kind of say, well, that's infrared, but it's close to microwave, so we'll call it the far infrared. Or this is a microwave that's, closer to being radio, so sometimes they'll call it a radar wave, even though it's in the microwave region. So just don't get the idea that these boundaries are set in stone. They can be, by law, people can set standards for different regions of the spectrum. But it's not like there's a change from being a microwave to an infrared wave in, it's a spectrum is what I'm trying to say. It's a continuum, and it slowly changes between these things. Okay. So we continue on our journey, talked about the long and the radio waves. You get through microwaves. Radar is just light bounced off of metal things, and you time the return trip, and you get how far away the thing is. Microwaves, we use these in our microwave ovens. We also use them for wireless. Our wireless routers are usually like 2.4 or 5.8 gigahertz. And so that is 5 times 10 to the 9. It's right in here, so kind of in this microwave region. Our phones also are on gigahertz type frequencies, so cell phones would be in this region. Infrared, these have enough energy per photon to actually get molecules vibrating. So to excite vibrational modes in molecules, if that means anything to you. And what those vibrations do is they turn straight into temperature. We interpret infrared light as heat light, right? Heat lamps emit a lot of infrared because they're very good at keeping things warm because they can excite these molecular vibrations. They're also used in remote controls for your TV, would use infrared. There's an infrared LED at the top of it, and your TV's just watching for that infrared beam. We can't see these, but this is what we emit. At the temperature that we're at, our bodies are constantly emitting infrared, and if you have an infrared camera, you can pick up a human body really easily against a cooler background. Alright, now we get to visible. This is where we're going to spend most of the time for the next few chapters, is visible light. This is usually what you think of when someone says light. You automatically think, oh yes, this is what helps me see. It's what, okay, maybe you don't think this, but it's what excites the molecules in my eyes and lets that chemical process happen in those cells in my retina in order to make sense of the world. The thing about visible light, what makes them special, the photons of visible light have enough energy to change the shape of molecules. Okay, so remember, infrared can make molecules wiggle. Visible light, these are just rules of thumb, but visible light can make molecules change their shape. And that's what happens in your eye, actually. You have these molecules called opsins that will change their shape. The retinal in them will change their shape from, I better not say, but from cis to trans or trans to cis, and then when they go back, or let's just say, that starts the chemical process that helps you see. Alright, so visible photons are special not just because we see them. It's a very nice range for chemistry because it can change the shape of molecules. Ultraviolet light is a little bit more dangerous, and you guys probably know this, because now you're getting into photon energies that can break chemical bonds. And there are some bonds that can be broken by visible light, but this is where you start to get worried because important molecules can be broken up by ultraviolet light. This is why they tell you to wear sunscreen. Who knows whether that's safer than the sun? I don't know. But it's so that you get less exposure to ultraviolet light, because if some important molecule, take DNA for example, if DNA breaks, then it may not always be able to come back together the right way, and you get a mutation, and you can get a cell that forgets how to die, and so you can get cancer from that. In fact, everything above this you would expect then, since the energy of a photon equals some constant times the frequency, you would expect all of the higher frequencies than ultraviolet to also be able to break chemical bonds, and that's absolutely true. In fact, when you get up to, ultraviolet has 10 to the 16 for the frequency. If you get into the X-rays, where you've got 100 times more frequency, you have 100 times more energy. This is just a constant called Planck's constant, if you care. We'll see it when we get to modern physics. So, X-rays, instead of just breaking one chemical bond, can go through like a freight train and destroy, say, 100 or 1,000 chemical bonds. So you want to avoid X-rays as much as you can. But there's a cost-benefit analysis that you have to do, because if you can find out what's going on inside a person's body without cutting them open, cutting people open also kills cells. And so we use X-rays for medical diagnostics. We also use them for treatment because of the way they can kill things. If you can expose a tumor to a lot of X-rays while keeping the surrounding tissue with a smaller dose, then you can actually do beneficial things. Even if you create new cancers, you can at least kill the tumor that you know about. And then gamma rays, these are extremely high energy photons. We'll learn about them when we talk about nuclear physics. Nuclear reactions tend to have much higher energies than chemical reactions by, something like 6 orders of magnitude more energy. So instead of dealing with a few electron volts per reaction, you're talking about a few 100 million electron volts per reaction. It's just crazy amounts of energy. And if you absorb a gamma ray, it's just bad news. It can, we're talking about, hundreds of millions of chemical bonds that can be broken by a single gamma ray. So these you want to avoid as well. This is one of the reasons why radioactive things are dangerous, because it really can kill your cells. And when they recognize it, they'll start the inflammation process and die. And you can actually get radiation burns from these gamma rays. So this is light in a nutshell. We don't always think of all of these different things as being related. X-rays being related to radio. That doesn't really cross our mind as our favorite radio stations pass through our head all the time. We wouldn't want that for our X-rays. But really, they are just different parts on this continuum of electromagnetic waves. They all propagate in this way. They are all created in similar ways just by wiggling charges somehow. And that's chapter 22.